Alright, here are some solutions from 1.09 and 1.10. The idea, of course, is that you've already attempted these, looked at the answer, reworked your problem, and if you're still wanting some clarity, now you're coming here. So let's go ahead and take a look first at a couple from 1.09. Okay, so our goal here is to show that the equation x cubed equals square root of x plus 4 has a solution on the interval from 1 to 2. So first, if we just think about this, this particular equation, and we notice there's only one variable, and if we are going to try and use inverse operations, we're going to run into some long sort of situation, and more importantly, we're not looking for the solution. We're looking to prove that it has a solution. And so in situations like this, what we want to do is think of a theorem that might help us. And that theorem is going to be the intermediate value theorem. And the reason that an intermediate value theorem is helpful is that it allows you to say, hey, are you looking to show that a certain function will be equal to a certain value? And if so, all you need to do is find a value that it hits on either side, make sure the function is continuous, and then you'll be able to say definitively that your function will pass through that point. So to make this a little more clear, what I want to do is think about this equation, x cubed equals the square root of x plus 4. And whenever possible, I'd like to have an equation where I've got all of my variables and everything on one side of my equation so that I've set something equal to 0. Because then I have some sort of function in terms of x, and I'm looking for when that function hits the x-axis. So what I can do here is I can subtract the square root of x plus 4 from both sides, and then what I'll have is x cubed minus the square root of x plus 4 equals 0. And in general, it's just a good idea to remember whenever we're trying to solve an equation, having something set equal to 0 is very advantageous. Whether it's a quadratic, being able to use the quadratic formula, or even a much more complex situation, we want to be looking for where the equation will equal 0. That's going to make our lives a lot easier. So now, just to give us sort of an idea of what we're looking for, we're looking to show that this function here at some point is equal to 0. Well, and to be more precise, on the interval from 1 to 2. So from 1 to 2. Okay? So what we're looking for is there any place where this function will intersect the x-axis in between these two x values. And with the intermediate value theorem, all we need to be true is that this function be continuous, and either at some point it goes from negative to positive, or goes from positive to negative. Okay? Because then we'll know for sure somewhere in between it has to hit the x-axis. So first let's check if this is continuous. It's a combination of a polynomial and a radical, so it is continuous. Okay. And now we just need to find some x values, that one which makes it positive and one which makes it negative. Why not just try 1 and 2, since that's the interval we're on? So what I do is I will name this the function f. And so now I'm going to check f of 1. And f of 1 is going to be 1 cubed minus the square root of 5. Well, it'd be great to know this exact value, but it turns out I really don't, right? I just want to know whether it's positive or negative. Square root of 5 is bigger than 1, and so this is going to be negative. Then I can go ahead and look for f of 2, Here I'll have 2 cubed minus the square root of 6. And this is, 2 cubed is 8. So 8 minus the square root of 6, well, the square root of 6 is in between 2 and 3, so this is certainly positive. So if I'm looking at my function, I know at an x value of 1, the function is negative, and at an x value of 2, the function is positive. So since it's a continuous function, the intermediate value theorem says there must be some value that makes it equal to 0, meaning there is a solution to this equation, and so therefore there is a solution to this equation. Okay? So what you want to do is practice writing that out. You need to mention, in order to use the intermediate value theorem, first off that the function you're using is continuous. Then you need to mention that both, you found 2 points, one negative, one positive, how that guarantees in between there must be a point that makes it 0, so therefore you have a solution. Alright, so this question wants to know, is there any real number exactly 1 less than its 4th power? So the toughest thing about this question, I think, is trying to figure out what exactly you're going to do to make this happen. And so it's easy to just sort of diagram, is there any real number? Well, I don't know what that number is yet, so let's call it x. Is there any real number? What do we know about this real number? Well, this real number is exactly 1 less than its 4th power, meaning this number is exactly equal to 1 less than its 4th power, meaning that number to the 4th minus 1. So what we're asking is there a number x such that this equation is true? Meaning, is there a solution to this equation? And so similarly, what we want to do is make this equation easier to work with. So if we can get it in, so that we have everything on one side set equal to 0, that's going to make our life a lot easier. And we can do that, and that will give us x to the 4th minus x minus 1 equals 0. And so now we can use the intermediate value theorem again, and again, here we actually don't care what the interval is. What we just need is some interval, some point A and some point B, and on that interval we either need to go from negative to positive, or we need to go from positive to negative, and so that we can guarantee somewhere in between it will be equivalent to 0. So again, name this your function f. F is continuous since it's a polynomial. It is continuous everywhere. Alright, so let's think about some values that might make this 0. Well, the most obvious one to me is 0. 0 minus 1. So f of 0 equals negative 1. And then let's see if 1 works. Let's think about it. 1 minus 1 minus 1. That's not going to work. What about 2? 2 to the 4th. Well, that's definitely going to work. So I have f of 2, which is going to be 2 to the 4th minus 2 minus 1. And 2 to the 4th is 16, so this is going to be some positive number. Doesn't even matter. It will be 13, so I guess we could just put 13, but it really doesn't matter. And so the intermediate value theorem says, hey, some x value between 0 and 2, when you plug that into your function, you're going to hit 0. It's guaranteed to happen because your function is continuous. So again, write up your answer, make sure you include the criteria that allow you to use the intermediate value theorem. Right? The function that we have here is continuous. You have a value, an x value 0, for which the function is negative, a value 2, for which the function is positive. Somewhere in between, there is some value c, for which the function is exactly equivalent to 0, meaning there is a solution to this equation, and so there is a solution to this equation. Okay, so this is another question about the intermediate value theorem. This tells you have a function f that is continuous, and continuous is very important. That means there's no jumping around, no discontinuity. And so between these points, it will hit every value in between them, if that makes sense. So to just give us an idea of that, so when x is 3, the value of your function is 20, and when x is 4, the value is 17. So since it's continuous, it will hit every value between 20 and 17. And then it'll hit every value between 17 and 12, and then it'll hit every value between 12 and 16, and then between 16 and 20. So the question is, how many times will your function have a value of 15? Right? Well, this is down here, this is 12, right? And so let's just think about it in terms of the intervals. Well, between 20 and 17, does it have to hit 15? No. Between 4 and 5, does it have to hit 15? Yes, it does have to hit 15. Between 12 and 16, does it have to hit 15 again? Yes, it does. Between 16 and 20, does it have to hit 15 again? Yes. So we have 2 times where it has to hit 15. Of course, it could happen more times, but the times we know for sure are 2. And so there's our answer. All right, find a value for a so that this function f of x, which is a piecewise function, is continuous. Okay, so remember with piecewise functions, if it's going to be continuous, we are going to check each part of the piecewise function first, then think about the possible points of discontinuity. In almost all cases, these are going to be the points where the function is switching from one definition to another. In other words, in this case, 1. So, of course, this is the case. Both pieces are polynomial, so they're both continuous everywhere. And so the question is, what will make them continuous at 1? Well, remember, for something to be continuous, the limit coming from the left as x approaches 1, and the limit coming from the right as x approaches 1 must be equal. So the first thing we need to do is set the limits, the one-sided limits, equal to each other. So we have the limit as x approaches 1 from the left. Now we have to be careful. From the left, which part of this function am I working with? Well, the left is the negative side, so when x is less than 1. So that's going to be x squared plus x plus a. Okay. And that needs to be equal to the limit as x approaches 1 from the positive side, and here we're using x cubed. Okay. And I guess I'll label it, this is criteria 1 for continuity. Okay. So let's just think about the right side. I guess that might be the easiest one to tackle first. Well, you want to find the limit. First things first, let's just see if we can plug in the value. Yep, we can, because 1 cubed is equal to 1, so it's continuous. Also, this is a polynomial. It's continuous everywhere. All right, so we get 1 over here. Now, on this side, we have this a value. What do we do with that? Well, remember, we're solving for a. We want to know what it has to be to make this continuous. This is a polynomial. It doesn't matter what a is, right? What constant a is. This will always be continuous as well. So we can plug 1 in to find the limit in addition to the right side. We can do it on the left side. So we'll have 1 squared plus 1 plus a. All right, well, 1 squared is 1, plus 1 is 2, plus a equals 1. And you may have guessed it, a must be equal to -1. Okay, so if a is equal to -1, then this portion becomes -1. And let's just make sure that those are going to be continuous, because the last thing we have to check for continuity is that when we plug in 1, we actually get the same value as the limit. So both limits, right, both limits are equal to 1, right? This limit's equal to 1, and now if we were to take the limit over here, it'd also be equal to -1. So now we just need to check what happens at f if we plug in 1, and here we're using this definition because x is equal to 1, and of course x cubed is 1. So we're good. All right, so the a value must be -1, and then we'll have both limits being equivalent to each other. If you don't believe me, go ahead and plug in -1 here, and when you insert 1 into your function, you'll get 1 plus 1 minus 1, which is 1. right? And so we found our A value. Okay, this is a true-false question that is central to the idea of what a continuous function is. So if you haven't gotten it, go back and read the definition of a continuous function carefully and look at the example that we went over in class. Then come back. Okay, so this says, can a continuous function, true or false, a continuous function cannot have a point of discontinuity. Okay, think about what this means. This is saying you have some continuous function, and no matter what, there's no way you can think of a continuous function that has a discontinuity. And this is false. And the reason is that a continuous function is a continuous function if it's continuous on its domain. It doesn't, if there's a value that is not in its domain, we don't care if it's discontinuous there. And the example of this is the function 1 over x. Okay? 1 over x, its domain is everything but 0. And if we graph it, it has an infinite discontinuity at 0. So it's not continuous when x equals 0, but that doesn't matter because its domain is all real numbers except 0. So it will go from negative infinity to 0, not including 0, and we can use union here. U means union, so it'll be this, and this means and, from 0, not including it, to positive infinity. So, false. Very important. False. Okay, this one's a little bit more of a doozy. We have this function f of x, 1 plus 1 over x to the x. And first we want to find the domain of f. Okay, well, the domain are all x values that will make this defined. And so it might be easier to think, what are the x values that will make this undefined? Well, obviously, 0 will make this undefined. Why? Because 1 plus 1 over 0 is 1 plus an undefined value, and so that won't work. Okay, so 0 is something that we can't have. Now, are there any others? Well, let's think about all positive values. All positive values are going to be just fine, right? Because you'll have 1 plus some fraction that's defined to some power. What about negative values? Well, just remember, for a negative value, if you have a negative exponent, what you're really doing is writing whatever you're taking to that negative exponent in the denominator and writing it to a positive exponent. So let's just consider negative 1 for a second. What would negative 1 look like? Well, negative 1 would be 1 plus 1 over negative 1 to the negative 1, which is 1 over whatever this is to the first power. Well, what is this? This is 1 minus 1, 0. So this is also undefined. So our domain, all real numbers except for 0 and negative 1. Okay. Now we want to explain why x equals negative 1 and x equals 0 are points of discontinuity. Notice these are both the values for which our function was undefined. Right? So why are they points of discontinuity? Well, there you have it, right? The function is undefined at both of those points, and so can't be continuous, right? A continuous function, when you're continuous at a point, the definition states one of the criteria is that the function is actually defined at that point, right? If it's not defined, then you're out of luck no matter what the limit is. So that's pretty obvious. C, are either of these discontinuities removable? So here, go back and remind yourself of what it means to be a removable discontinuity. For a removable discontinuity, you have the limit exists, right? The limit exists. The problem is that the limit that you get is not equal to the function value. Well, the function value is undefined at these points, so obviously it's not going to be equal to the function value, but the limit might still exist. So let's go ahead and find the limit. So you can find the limit as x approaches negative 1 from the left, and the limit as it approaches negative 1 from the right. Now, how are we going to find the limit of this as it approaches -1 from the right and -1 from the left? Well, my advice to you would be to go through your various protocol, right? So first plug in -1. What happens there? Well, you get something that's undefined, right? Okay, now maybe you then say, okay, let me move on to to algebraic manipulation. This doesn't look like anything we've seen before, so you give up there. The fail-safe plan is to use a tabular method, right? Make a table as you approach -1 from the left and as you approach it from the right. See what the values are getting closer to. If they're the same, then the limit exists, and that's its limit. Now, what I want to do is show you a kind of sneaky way of doing this, finding this limit without making a table. And here's how. Go back to looking at what happens when you plug in -1. Okay? When you plug in -1, because it's a negative exponent, this piece here moves into the denominator. In other words, the numerator, basically you have a rational function where the numerator is going to be 1. Okay? Which means in the denominator, you're going to have some value. What's happening to this value? Well, as you get closer to -1, it's getting closer to 0, right? Let's think about how it gets closer to 0 as we move from the left side. So from the left side of -1, you're going to have negative values that are more negative than -1. Meaning, for example, you'd have 1 over, let's say, -1.1. Well, that's a value that's less than, in absolute value, less than 1, right? So you're going to end up with a positive value. Okay? So you're going to be, as you move from the left side, you're going to be approaching infinity of the positive variation. How about as you approach from the right side of -1? Well, from the right side of -1, you have values like -0.9. Okay. Well, 1 over -0.9 is a negative number that's bigger than 1 in absolute value because the denominator is smaller than the numerator. So here, you're going to have 1 minus a value bigger than 1 that's getting closer to 0. So it's going to be approaching negative infinity. Okay? So from the left, approaching positive infinity. From the right, approaching negative infinity. So our limit does not exist, right? We have an infinite discontinuity. And in fact, we only had to find one of them to know that it was going to be an infinite discontinuity, but finding both of them was just kind of helpful depending on which way you started. Okay? So x equals -1, not a removable discontinuity. What about 0? So for 0, if you plug in 0, you get something that's undefined. And what I encourage you to do there is to make a table of values for what happens as you are approaching 0 from both the left and the right, and you'll find that you are approaching the same value. So it is a removable discontinuity at x equals 0. All right? Next, you want to use graphs and tables to estimate the value as the limit as x approaches infinity of this function. And this is really, really interesting. So I encourage you to go on Wolfram Alpha or your calculator and graph this and look at really big x values, and then to make a table of values that get very, 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 very large. Okay. And what you'll be noticing is that f of x is going to be approaching a very famous value. Okay? In fact, that famous value is going to be the value e, which is approximately equal to 2.718, so on and so forth. Right? You can look up Euler's constant on your own. Okay? And we can talk about this a little more if you're interested. This is, in fact, the way that you compute Euler's constant is by taking the limit of this function as x approaches infinity. And one way of thinking about this is actually infinitely compounding interest, continuously compounding interest. In other words, you're going to compound some value of interest on an investment, for example. But you don't want to just compound it at the end of every year, right? Because then someone might take advantage of that and wait 11 months to pay you back, but then right at the last minute they'll pay you back before you've put the interest in. So what you want to do is you want to actually compound interest every instant, so that by the end of the year you've compounded a total of 5% or whatever it is, and this will allow you to compound interest infinitely. So if you use this as the base, if you use Euler's constant as the base of an exponential function, you'll get some cool work with continuously compounding interest. And that's something that you can take a look at. I think your book might even talk about that in chapter 1 or whatever the pre-calc review is. Okay, hopefully this was helpful and cleared up any misconceptions that you previously had.